Let's continue. Before we go, we just quickly talk about the van der Waals force. Again, this is not a chemistry class. We are not going into the detail. We'll just refresh our mind a little bit. Okay, it's what? Primary bonding or secondary bonding? Secondary bonding. The primary bonding are metallic bonds, covalent bonds, something like that, right? Or ionic bonds. But van der Waals force are secondary bonding, existing between all atoms, molecules, and including ceramic particles we are dealing with here, okay? And the categories that would include the force between permanent dipoles, that people call them Keeson forces. For example, between permanent dipole, between these polar water molecules, or between polar HF molecules, or between a water molecule and a HF molecule. These are between so-called permanent dipole because each of these molecules you can clearly identify which portion is kind of more positively charged, which part is more negatively charged. It's not symmetric from charge point of view. And because they are not symmetric, they would have so-called permanent dipole, and between individual molecules that will be so-called van der Waals force, Keeson force. Okay, let me pause. So as you see, these types of molecules, water or HF, because there's strong polarity in the molecules, they bond strongly, and as a result, compared with other similar molecular weight molecules, they have a much higher boiling temperature, much higher melting temperature. For example, if we think nitrogen, and nitrogen would, I'm going to let me first finish this. The force between permanent dipole and induced dipole is people call it the biforces. For example, between HF and hydrogen molecules, right? Hydrogen symmetric. Two, you can only covalently share electron. It's not a clear dipole moment within it. HF clearly have one. Between these two, they would have the biforces. Weaker than Keeson, but stronger than the other one, which is so-called dispersion force between completely transient dipole, between London forces, between completely non-polar molecule, and we give okay between individual hydrogen molecules or between individual nitrogen molecules. Let's see, okay, water molecular weight 18, for example, the water melting temperature 0 degrees C, right? And the boiling temperature 100 degrees C. But similarly, when you think of nitrogen, liquid nitrogen temperature going from gas to liquid, the boiling temperature is 77 K. You think how much temperature difference? It's a very dramatic difference between the boiling temperature. So that's kind of like you know the fact, you know the chemical properties, and then you have an idea of why they are behaving like that. But in terms of imaging, it's difficult, especially imaging which part is positive charge with a negative charge. Imaging it almost become impossible. But at the same time, that's where your imagination, your theoretical part comes into play. Because in molecule, we don't have a good way to image individual molecules, especially small molecule. Large molecule, they have hundreds of atoms, people can image it. Like a protein, people can image it. But single molecule, like one atom, two atoms, yeah, the quantum effect will kill you. Okay, so the magnitude of these forces are quite often, as we mentioned, that they are low, but how low depending on whether there's permanent dipole involved. Okay, and the generally the potential energy for van der Waals force, they generally satisfy 1 over distance to the power of 6, which is pretty weak. Pretty weak. Okay, and if we're going to describe it a little bit further, where people do model, and we're not going into the detail for the model, but we just describe the concept a little bit. For example, assume the interactions between Here we are talking about particles. We say van der Waals force exists not only between atoms, between molecules, but also between, here in this class, we are dealing with material, between two solid particles. Okay, if the interaction between two particles, we can sum it up as the interaction between very small units within the particles. Okay, the interaction between the small unit within one particle against another unit in the separate particle. As we draw here, we have particle 1 on the left, particle 2 on the right. Okay, if we define a few terms, one is, okay, if we have a small unit within particle 1, we call the volume delta V1, so-called infinitesimally small, very small volume unit. In particle 1, we call it V1. And in particle 2, of course, we can define delta V2, right? And the N1, the number of atom number density within particle 1, which means per unit volume, how many atoms within particle 1. And similarly, N2 would be atom number density within particle 2. And if we define the distance between the unit, small unit that we choose in 1, small unit that we choose in 2, if we define it as x, the distance of x, then the potential energy between these two small units, not the two big particles, but the two small units, if we can kind of write it something like this. Constant over the distance. Because they are relatively small, we can fix the distance, kind of x to the power of 6, and then volume times number density, how many atoms, volume times number density for the other particle. So this gives us the total kind of potential energy. Okay, and then the total interaction energy. Total interaction energy between what? Between one entire particle and the other entire particle would just be the so-called summation, or if we do integration over the entire volume, right? If we just write something like this, over the entire volume. Here we will not go into the detail, but we'll just say, okay, a previous scientist, Hamaker, showed that the typical potential energy would take the form something like this. A constant over pi to the power of 6 integration of the volume 1, volume 2 over the distance to the power of 6. And the first term before the integration is so-called material or system specific, depending on what material we have, polar, non-polar, whatever. The other part is completely geometric, right? You just integration over the volume. And if you have different particle size, particle shape, or different distance, you would have different geometric term. Okay? And this A constant is called Hamaker constant. And it's material or system specific. Now we have special cases. If the two particles are kind of like flat surface separated by a uniform distance of h, kind of people can derive the potential energy as something a constant over pi h square. Over pi h square. Of course, in this case, it would be kind of potential energy per unit area. Make sense? It will be per unit area because depending on how large I go up and down, the total potential energy, of course, will be different, right? So as a result, this is A over h to the power of 2 per unit area in this case. Another case, okay, if we have just one particle, but the other side is infinitely large. I have radius, I have distance between the two, and in this case, if what? It's a very large sphere, large particle compared with the gap between the particle and its flat surface. If we satisfy this relationship, the energy would satisfy here. Okay, now it's kind of unrelated, the A over 6 R over H, related to the relative size. Okay, on the other hand, if we just have two particles, two what shape? Perfectly spherical particles, same size, same radius, separated by small h from surface to surface, or separated by big capital H from center to center. Okay. Of course, this capital H is small h plus what? 2r, right? That's just the thing. When the distance, the gap is much smaller than the size, we would have one expression. When it's the other way, the two particles are very, very, very far away, we would have another expression. But anyway, we will not go into the detail how we derive that because we are not chemistry class. Okay? So people get these types of potential energy. And generally, the so-called Hamaker constant, people determined it is very small number, 10 to the minus 20 joule. That's just for A, for that A constant. Okay? Hamaker constant would decrease if between the particles it's not vacuum or air, but some other types of medium. Okay? Here we give a list. We give the different what? Types of particle or material. And then we listed the so-called crystal structure. And we gave the table listed the so-called Hamaker constant if they are separated in where? Vacuum. Okay, which for air is probably the same. And then the number would be much smaller, but not too much smaller, by a factor of 3 or something like that, if they are separated by a medium, in this case, water. Okay? So table like this exists for some material, not all material, for some material, for some solvent, not for all solvents. Okay? But anyway, let's go back. This is what we have. In our kind of colloidal suspension, right? Fine particles separated by h distance. Okay, small particles. And if we assume the equation hold for potential energy is valid down to contact, and if we say, okay, the particles are separated by a small distance, 0.3 nanometer, 3 angstrom, pretty small, which means when the particles get in pretty close to each other, separated by a few atoms, when they get very small, generally our particles, if you have to guess, the radius would be higher or comparable to this number. General particles. No, general particles will be way ceramic particle, right? You are talking about ceramic actual particle. We are talking about, okay, quite often 1 micron, 0.1 micron, which is 100 nanometer to 1000 nanometer. The gap here, okay, if we say when they get very close enough, 0.3, so we would satisfy the relationship of h, much smaller than radius. If it is this, we would have such a relationship. Which means when the two particles getting very close to each other, we can roughly calculate their so-called potential energy. Okay? And if we know the Hamaker constant for, okay, more or less the material is on this order. We don't go into specific material. We just say it is more or less on this order. Okay? Then the van der Waals energy between the two particles depends on, if we know h is given by this number, if we say we know the A, the Hamaker constant is on this order, then it just depends on so-called the particle radius, right? Particle size. And if it's 200 nanometer, we plug the number in. We would get, okay, a potential energy between two neighboring particles of this magnitude. On the other hand, if we say our particles are even smaller, even finer, nanometer, real nanometer, 20 nanometer particles, the potential energy, you are doing the same thing, right? You just plug a different radius number here, right? Instead of 200 nanometer, you plug 20 nanometer, and you get a 1/10 of the so-called van der Waals energy or potential energy between these two particles. Negative means they are attractive. They are attracting each other. Okay? That's what we say. And then we are going to do a comparison between this so-called attraction energy or this van der Waals energy and so-called thermal energy. Okay, thermal energy. We say at room temperature, generally when you handle your colloidal suspension, out of a special occasion, generally you are handling them what? At around room temperature. And the general thermal vibration energy, generally, we are not going into precise, but generally they are on the order. Pay attention to what I say. We're not doing anything precise. We'll just say estimate they are on the order of kT. That's the individual atom that has the thermal vibration energy that would knock the particles. That gives the particle that knock. How much of a knock? It's this kT. And we know K is what? Boltzmann constant, and T, room temperature, you know T. And as a result, if you plug this number in, KT, K, Boltzmann constant, and T, 298K, you would get also a number, but, okay, it is this number, kinetic energy. Remember, this thermal energy is essentially vibration. It's a kind of kinetic energy. It is something that you imagine one molecule struck the particle, and your particle got struck. Your particle has absorbed that kinetic energy. It's going to move. And what we see is important thing would be this one. The kinetic energy compared with what? To the van der Waals attraction energy is what? Much smaller. What does that mean? The implication would be, okay, if the two particles, if they somehow stick together by the van der Waals force, the thermal vibration energy, the thermokinetic knocking energy by the molecules, liquid molecules within your suspension is not enough to overcome it. It's not enough to overcome it. I'll put it the other way. The probability for a two particle to be knocked separate by a thermal vibration due to the molecule, liquid molecule, is almost zero. Once they stuck, they stuck. The thermal energy is not enough to knock them away, knock them separate. This kind of is the fundamental reason that, okay, for most ceramic particles, if they are not charged, when they are fine particle, we say 20 nanometer, 200 nanometer, whatever. Okay. When we don't worry about gravity, they are fine. So we don't really worry about gravity. We can calculate. You can calculate the gravity energy. You can do the same thing for assuming certain density. You can calculate the gravitational force or energy, and you can compare. You would notice the thermal energy is kind of enough or comparable to the gravitational potential or energy, but it's not enough to overcome the van der Waals force. Okay, so that's the reason, okay, for this type of colloidal suspension, we worry less about direct sedimentation, but we worry about this so-called flocculate, form so-called soft agglomerate between individual particles, become a larger cluster. Okay, so that's kind of an estimation that help us to understand the phenomena that we see in